Let's start. Good morning, everyone, and we start fall semester. And in this semester, we will continue to study the course of linear algebra. And the previous semester, we considered the vector spaces, but now we are going to consider the mappings between vector space. What does mean natural mapping between two vector spaces? If we have vector space, I recall that vector space be the set with two algebraic operations. First of them is called vector addition, and the second scalar multiplication. If we have natural mapping between such objects, naturally suggests that this mapping preserves this operation, and this very natural condition. And we will suppose that the mapping between two vector space satisfied these two conditions. And such mapping we will call linear transformation. The other title for the vector space, the linear vector space, and the operation in the vector space as a rule called linear operation. And this reason that this title for such mapping, linear transformations. First of all, let's start with very simple example. Maybe you can say the maybe simplest example of the vector space. Can you help me and say what's the maybe one of the most simple example do you know? Sample example of the vector space. Can you suggest such example? No. Addition is algebraic operation. But what does mean vector space? But yes, vector space is a set with such two operations. When we tell about vector space, we mean that we have, first of all, we have basic field. In our example, basic field will be maybe real number field R, and second example of the basic field, complex number field, which denoted by C. And what does mean vector space? Vector space V is the set with two operations, vector addition and scalar multiplication. Vector addition satisfies the four following axioms. First of these axioms, commutativity. Second, associativity. Third, existence of zero. Exists such element of the vector space V such that A plus 0 equal A for all A from V. And fourth, existence opposite element. For all A exists such element minus A, Z A plus minus A is equal to 0. For axiom for addition. To axiom for scalar multiplication. If I multiply unit of the field on arbitrary element of the vector space A, we obtain this element A. If we have two scalar mean the element of basic field only, the element of the basic field. If you multiply two elements of the field and multiply this point mean multiply of scalars, this point multiply on the vector, scalar multiply on the vector, scalar multiplication. We have scalar and vector, and if we apply this operation, we obtain the vector. Sorry. And we have two axiom so-called distributivity, the axiom which connect scalar multiplication and vector addition. First of all, if we have a scalar lambda and two vector A and B, we obtain the following equality. If you add two vectors A and B, and after they multiply on the scalar lambda, we obtain exactly the sum of the two vectors. First of them is scalar product of scalar lambda and first vector A, and second summons is a scalar product of the scalar lambda and the second vector B. And the last axiom, if we have two scalar lambda and mu and multiply on the vector A, we obtain the sum lambda times A plus mu times A. If these axioms fulfilled on the arbitrary set with the operation, we have the vector space. And the most example of the vector space, basic field R, for example R. Easy to see on the R defined multiplication and define the addition, and we can identify the vector addition and addition in the basic field, and we obtain the simplest example of the vector field which coincides with basic field R. After them, more yes. Yeah. I use Greek letters lambda, mu, and by these letters I denote the element of the basic field in our example R, and Latin letters A, B, the vectors. Yes. We have the following 8 axiom. This abstract definition of the vector space. Any set with two abstract algebraic operation which satisfied this axiom we called vector space. Very abstract. Nothing. Do you understand it? But we have some basic examples of the vector space, and we will deal with examples. First of them. The simplest example, the basic field. First of all, we fixed basic field, and after them we have deal only the vector spaces over this vector, this basic field. We fixed vector space, basic field.
What do you mean by saying basic field?
Basic field, the first ingredient. When we define vector space, we start with some ingredient which we called basic field. In our example, basic field may be a real number field or complex number field. We must demand from this basic field the following assertion properties. In this basic field must be defined two operations, scalar and multiplication, and this operation must be satisfied the following axiom as in the case of the real number or complex number. The main properties, we must divide one element on other, and after them we obtain the element of this field. Field is some algebraic construction. In our example, field only real number field or complex number field. But exist many other examples of the field. In other cases, we also can define the vector space over this other field. This more.
So instead of real numbers, I can use, for example, integers or.
No. Integer not field. Why? If we have two integer, for example, 2 and 3, and if we can ratio to number, this is not ratio, not integer, the rational number. But rational number is a field, and we can also extend this example and consider also Q, the rational number field, is also the maybe simplest example of the basic field, the so-called simple basic field. We have following inclusions. This one belongs this one, and this one belongs this. This so-called algebraic closed field. What does it mean basic? Basic does mean that we consider the vector space over this basic field. It does mean that we consider scalar only from this basic vector field, from basic field. First of all, we fix basic field. We are going to consider some general construction, and I will denote basic field by K. K be a basic field. For us, K maybe a real number field or complex number. And second example of the vector field, the so-called arithmetical vector space. The element of this vector space be n tuple a1, a2, an. This element of this n tuple be element of the basic vector field. And on this set, we can define two operations, vector addition, by the following formula. If you have two n-tuples a1, a2, an, and second b1, b2, bn, the yeah. Mm-hmm.
Wait, hello, good morning.
Good morning.
I cannot see the word what you wrote right now.
Ah.
Not clear.
Yeah. Maybe. Yes. Mm-hmm. I call some simple example of the vector space. If you have basic field K, we can introduce the so-called K up n, the set of the n tuples of the element of the basic field. If K be a real number field, in this case we have the n tuples of the real numbers, and we can define operations of the vector space, vector addition, by the following formula. If we have two such n tuples, I can define the vector addition of these n tuples. The n tuples, each element of this is the sum of the corresponding element of adding n tuple. The first element of the sum is equal of the sum of the first element of this summons the second of the sum of the second element, and so on. For example, if n is equal to and first three tuple 1, 0, 2, and second minus 1, 1, 1, the sum of these three tuples is equal 0, 1, 3, distant, and we can define scalar multiplication by this following formula. If I want to multiply scalar lambda on this n tuple, I must multiply each element of this n tuple onto this scalar. And I obtain the following n tuple. For example, n is equal 3, 1, 0, 2, and I want to multiply on this number 3. I will obtain 3, 0, 6. 3, 0, 6. This most the enough simple but very important example. The main idea of the consideration the following: the arbitrary vector space can be reduced to this example. What's the way? How we can reduce the arbitrary vector space to this simple example? Almost almost every exactly finite dimensional vector space. I recall that the basic notion of the vector space theory is the notion of the basis in the vector space. What does it mean, basis or base? Maybe everyone explain linearly independent and
such that if there is lambda 1 plus
Mhm.
1 plus lambda b, ab,
Mhm.
plus lambda n
Yes.
equal to 0.
Mhm.
And
Linear independence, what does mean linear independence of the vectors? If you have the vectors a1, a2, and an, this set is called linear independent if and only if its linear combination equal 0 only when this constant lambda 1, lambda n all are equal 0. It does mean linear independence. The first property of the basis. And the second property, what does mean second property of the basis? Basis in the vector space. The second property does mean that basis is a generating system. What does it mean, generating system? If we have arbitrary vector of the vector space, this vector can be expanded in terms of these vectors. Exactly, it does mean that exists linear combination of this vector which is equal this vector v. And these numbers v up 1, v up n unique defined. The existence following from the fact that this system is generating, but uniqueness of these coefficients is the consequence of the first property, linear independence. How to deduce uniqueness of these coefficients from linear independence? Maybe you can explain how deduce uniqueness of these coefficients from linear independence. Suppose that we have two such decomposition. We have two various decomposition of these vectors. And I can consider difference between this decomposition and this. And this difference is equal exactly 0, because we have inside two vectors v. And I can use the axiom of the vector space and obtain that this difference is equal exactly the following sum, the linear combination of the vector a1, and these coefficients, area of these coefficients is the difference between corresponding coefficients of these two linear combinations. And this vector are linear independent. What does it mean, linear independent? In correspondence of this definition, we obtain that these all coefficients are equal 0. Equal 0. It does mean exactly that these corresponding coefficients are coincide, and we have uniqueness of this decomposition. Basis, such system of the arranging system of the vector in the vector space such that first, every vector of the vector space can be decomposed, can be expand in the terms of the vector of the basis, and this expansion is unique. This expansion is unique, and the coefficients of such expansion are uniquely defined, and these coefficients are called coordinates of the vector A in the basis A1, A. So, thus, we obtain the corresponding between arbitrary vector space and the arithmetical vector space. This correspondence is defined by choosing of the basis in this vector space. These correspondence are not uniquely defined. This correspondence defined by choosing of the basis, and this correspondence PE defined by the following formula. We start with some basis E1, En in the vector space V, and if we have arbitrary vector of the vector space V, we can expand in the terms of the vector of the basis, and this expansion uniquely defined, and we can correspond to this vector the coefficients of this expansion. And we obtain n tuples, the element of the arithmetical vector space. And this correspondence has the following properties. We will denote this n tuple by V with sub index E. E does mean the basis in the vector space. And if we have two vectors V and U, and if we consider the sum of this vector and consider the coordinates of this vector, we exactly obtain the sum of the corresponding coordinates vector, the first property. And the second property, if I multiply the arbitrary vector V on the scale lambda, and after them I consider the coordinates of this vector, I obtain exactly the product of this scalar lambda on the coordinates of the vector V in the basis. I recall how to prove these two properties. First of this property. If I have sum of two vectors v and u, easy to see if I expand the first vector in terms of the vector basis, I obtain the such sum. If I obtain the second, I obtain this following sum. But using axiom, this I can use the axiom of commutativity and distributivity, and I can rewrite this equality in this following form. Why this equality is fulfilled? For example, if we have if you have n is equal to the first sum v1 e1 v2 e2, the second sum u1 e1 u2 e2, and I can use commutativity and transpose these two vectors and rewrite this equality in the following form. After them, I can use associativity to rewrite this equality in this form. After them, I can use the distributivity law, and I can present the first summand in the following form: v1 plus u1 multiply e1 plus v2 plus u2 multiply e2. The first summand is equal this one, and this summand is equal this one. In arbitrary, in the case of the arbitrary n, we must apply induction reasoning by induction, and I check this equality in the n is equal 2. After them, I suppose that equality is fulfilled for some fixed n, and I can I must check for the next values of the n is equal n plus 1. For this summand, this equality is fulfilled by induction, and from this I can repeat this reasoning, and I obtain strict proof of this equality. We checked the first equality. The same way we can check the second equality, and we obtain that exists mapping between arbitrary finite dimensional vector space. Finite dimensional does mean that in this vector space exists finite basis, and such vector space Kn. And this correspondence the following. We we start with arbitrary vector v, and to this vector v corresponds some n tuples of scalar. This scalar exactly coordinates of this vector in the basis v. The first main idea in the vector space theory. Yes, yes. An example. Yes. Then maybe one. Okay. Maybe the following example. Let's consider the vector space of the polynomial with degree less or equal n. Oh, less or equal to. What does it mean polynomial? I consider the, for example, basic field will be R, real number field. And I have the following maybe function is defined by this formula, and in this case t be variable. And I can consider this expression as a formal expression with formal variable t. And I can define the sum to polynomial. I can consider the sum as the sum of the function, and I the same way consider the sum of the polynomial as the sum of a formal expression. If I have b0, b1 t, b2 t square, and I can obtain the sum of the polynomial by the following formula. And the same way I can obtain, or I can define the scalar multiplication in the set by the formula. And in this case, we obtain the vector space is called R, T, and symbol 2 means that we consider the polynomial with degree less or equal to. And in the general case, I can write any integer n in this case. I obtain the vector space, so-called vector space of the polynomial of degree less or equal n. And I can choose the basis in this vector space. For example, I suggest the basis a1 t squared. If I have the such basis, I can correspond to the polynomial f a1, a0, a1t, a2t square. We have linear combination. Natural. I can imagine that this polynomial is a linear combination of this monomial, and by definition, this scalar will be coordinates of this polynomial. You consider this polynomial as a vector of this vector space, and these coefficients became the coordinates of these vectors in this basis, and I obtain mapping from this vector space, this vector space, to this coordinate vector space R3. In general case, if we start with a vector space of the polynomial of degree less or equal n, we obtain the isomorphism in the vector space R up n plus 1. But I can choose other bases. For example, basis U. For example, 1 T is pre-divided 2. And in this case, I obtain other coordinates, and I obtain other correspondence. I can choose the third basis. For example, U tilde 1 t minus t0 t minus t0 square. And in this case, I obtain the third decomposition of this vector. If I have polynomial ft, I obtain the following decomposition: ft0 plus f prime derivative plus the second derivative and using the so-called Taylor expansion, I obtain that in the third example, the coefficients the following. And I obtain the values of these polynomials in the point which is equal t sub 0 is equal a1, a1 t0, a2 e0 square. The first coordinates of this expression. The second, a to 2, G0. Plus the second derivative 0, 0. Oh, I'm sorry. Yes. Without. That. And in this case, and we obtain the following expression. And we obtain the coordinates of this polynomial in this basis. We can see that if we choose the base in the vector space, we obtain the various correspondence between initial vector space V and arithmetical vector space. We obtain the various mappings. The mappings defined by the choosing of the base in the vector space. And we stress this fact using notation pi sub e. E denotes the base. I recall the basic fact of the vector space theory. And yes. Question.
What was phi?
Phi denotes the basis in the vector space.
What about E?
E is the basis. Phi, the mappings, the coordinate mappings. I repeat the main definition. The main construction of the vector space theory is the following. I repeat this main construction. We consider the example of such construction, but totally briefly we can briefly repeat this construction. I start with arbitrary vector space V, and I choose the basis E in this vector space. I choose and fixed some basis. After them, I can define the mapping from V onto arithmetical vector space Rn. The mapping is defined by the following way. Yes, I can choose the arbitrary vector V from capital V, capital V vector space. Small v, the vector. And after them, I can expand this vector in terms of the basis. I obtain such expansion. After them, I correspond to this vector, these coefficients, these coordinates. These coefficients is some n tuple. and I obtain such n tuple. And this n tuple is the element of this vector space. And I define the correspondence, which we start with arbitrary vector v and obtain some n tuple. Vector v is the element of arbitrary vector space, and this n tuple is the element of the arithmetical vector space. So I change the arbitrary vector space by the arithmetical vector space. But this correspondence defined by the choosing of the base in the vector space. I have infinitely many such correspondences. But if I fix one of these bases, I have infinitely many bases. But if I have these bases, I fix this correspondence. If I choose the basis, I choose these coordinates. How to describe, how to change the coordinates of the vector if we change the basis? I recall, if we have two bases, E prime, the old basis and the new basis, and I have some transition formula from one basis to the other. I have the following formula. We express the element of the new basis in terms of the old basis. And we written this system of linear equation in the matrix form. I use this matrix. We use this matrix notation, and we can write this formula in the following matrix form: E times C is equal E prime. This basis I denote by E, this basis E prime, and this matrix C. And I can rewrite this formula, this long formula in this short form, in this matrix form. Vector V I can rewrite in the following form. I use row column matrix multiplication. How we multiply row on the column? I recall that we multiply the corresponding element and after them to add the summands. And this sum is, can be written in the following matrix form. And I use notation E from this, and V is index E from this column, and this notation from this row. The element of this row vector, the element of this column are scalar. I can multiply scalar on the vector, and the product is the sum vectors, which exactly is equal to V. After them, I can rewrite vector V using old basis and new basis, and I have such equality. After them, I can substitute from this equality, I can express E prime in the term E, and I obtain and I have this equality. This one is equal to this one. But E will be basis. It does mean that the expansion in terms of the basis vectors is unique. It does mean this coefficients is equal to this coefficients. We obtain the following formula. This formula gives us the expression for coordinates vector in the old basis in terms of the coordinates in the new basis. The transition formula from coordinates of the vectors in the new basis to the coordinates of the old basis. I stress that we start with formula which gives us expression of the new basis in the terms of the old. But for coordinates, we have opposite expression. Coordinates in the old in terms of the coordinates in the new basis. Two dual formulas. Okay, that's the main basic properties of the vector space theory. But now we will repeat this main property for the linear transformation. Namely, first of all, we consider the simplest example of the linear transformation, this analog of the arithmetical vector space. The canonical presentation for the linear transformation, which will be analog of the presentation in the form of arithmetical vector space. This presentation is exactly, I can present linear transformation as a matrix. Matrix is a canonical presentation for the linear transformation. Transition formula for the basis. We have two bases in the vector space, one of them old and the new. And we have expansions for the vector of the new basis in the term of the old. I can rewrite this formula in this matrix form. If I multiply this row on this column, this one on this one, this one on this one, I obtain exactly the first expression. If I obtain this row on the second column, I obtain this expression. This one is equal to this one in corresponding on this form. This on the second, this second. The last, the multiplication of the this row on the last column. As a result, I obtain the last vector of the new basis. And this formula exactly equivalent of this. After them, I can rewrite this formula in the matrix form. I change this and tuple by this this matrix row. E does mean matrix row. C is a matrix. E prime is matrix row. Okay. After that, I can use this formula for expression of the coordinates vector in the old basis in the terms of the new basis. How? I can rewrite the formula of expansion of the vector in terms of the vector basis also in the matrix form as a row column product. And I can rewrite this formula in this in offshot form, in the offshot matrix form. After them, I have expression from the vector in the terms of the coordinates vector in the old basis and the new basis as a row column products in this form. After them, I substitute the expression for the new basis in terms of the old in this expression. I change this E prime by in correspondence of this formula. And after them, I use associativity property from the matrix product, and I obtain this formula. This formula does mean exactly the expansion of the sum vector on the vector of the basis, and this row and this column, and element of this column the coefficients of such decomposition. But this basis and this column is uniquely defined. But if we have two expression from vector v, two expansion in terms of the vector basis, this expansion by definition of the basis must be coincide. And from this it follows that this column coincides this. And I obtain final formula for expression of the coordinates of the vector in the old basis in the terms of the coordinates in the new basis. And the main ingredient of this formula, transition matrix T. But this matrix acts in dual acting from this. This new in terms of the old, this coordinates in the old in terms of the new.
And then the matrix will be the same, right?
The same, exactly same. But acting of this matrix is dual. In this matrix acts on the right side and this in the left side. Dual act. If you apply operation transpose, and rewrite these rows as a column, we obtain this C transpose of the matrix C. This column, this row, if you apply transposition, we obtain this transpose of this matrix. The acting dual in these two cases, dual one to other. Okay. Yes, it's the main fact from vector space theory. And now we try to transfer this fact, generalize to the linear transformation, to the mappings. And first of all, we start from the following example. Let V be arithmetical vector space R2, and we can consider the following mapping from R2 to R2. The mapping which defined by the matrix F. If V be the vector from the R2, I correspond the vector V matrix product matrix F from the vector V. If V V1 V2 corresponds this vector matrix product of the matrix F on this vector V, and as a result I obtain the following vector easy to see. The matrix multiplication has the properties of distributivity, and if we have two vector u plus v and we multiply from the left side on the matrix F, we obtain, using distributivity property, we can to check this formula on this example. If I change v1 v2 on the sum v1 plus u1 v2 plus u2 in this expression, I obtain the sum of the corresponding element, and after them using definition of the matrix addition, I obtain this equality. And the second property, if I multiply vector v on scalar lambda, I obtain product of scalar lambda on the image of the vector v on the mapping F. I obtain the main property. I stress that the property is the same as the property mapping phi sub e, coordinate mapping. The same property of linearity. And after them, I can define the main concept of our course, the linear transformation. Linear transformation. What does mean linear transformation? The definition. This definition is direct generalization of the property of this mapping. This main example of the linear transformation, the main example. And as we will see later, this example enough general, maybe most general example of the linear transformation. The almost arbitrary linear transformation can be reduced to the transformation of such type. This analog of coordinate presentation of the vector. Definition. We fixed some basic field K. And let V W be the vector space our K. The mapping F from V to W is called linear transformation. If this mapping has the two following properties. First of them, property linearity, for all V from V, and the second, homogeneity, so-called property. That's all. This full definition of the main notion of the theory of mappings between linear spaces. Definition of the linear transformation. Only these two properties define this construction. I have maybe 1 or 2 minutes, and my lecture now will be finished. But before end, I try explain. Сколько времени? Сколько? 10. Сейчас здесь 23, заканчивается в 10:25. 2 минуты. I have 2 minutes. And during those 2 minutes, I try explain the plan of our study. The main idea of user reasoning is the following. We have two vector space P and W and mapping F. Maybe 5-10 minutes before, I define the coordinate isomorphism. I can choose the basis E in the vector space V and the basis U in this vector space W. And I can consider coordinate isomorphism E from arithmetical vector space Rn. And this one, coordinate isomorphism U to the arithmetical vector space Rn. And what I obtain in these rows, what the mappings disclose this commutative diagram. The answer is following. The sum matrix P, E, U. And this matrix, which can be defined as the following way, I can obtain inverse mapping PE. After I can apply mapping phi, and after them I can apply other isomorphism PU. As a result, I obtain some linear transformation from this vector space to this vector space. And this linear transformation in all cases is easy fact. Is transformation which is defined as multiplication on the matrix. And this matrix phi EU. And this matrix of the linear transformation. What's the moral of this fact? I reduce the arbitrary linear transformation to the partial case of such transformation, the multiplication onto the matrix. And this matrix is analog of coordinates of the vector, the main fact. And on the next lecture, we consider in detail this fact. Thank you for your attention. Maybe question.